Welcome back, guys. Continuation of previous topic asymptotes. We have this topic curve tracing. For tracing of a curve, we have to follow these four steps. First one is symmetric. We have to check the symmetric of an curve. It's symmetric about what we call axis or line, something like that. And we will find and we have to check about origin. Where is it located? Is it passing through origin or it's passing something away from origin or like that? And we will try to find asymptotes of the given curve, and we will try to check where the asymptotes, and we have to check the points, uh, the points of the point where the tangents are parallel, tangents are perpendicular, and the points where the what we call it touching the axis and crossing through another axis. These are the basic things we will discuss in detail now. If you want to check symmetric about, if you want to check the symmetricity about x equal to 0, that means y axis, just keep x equal to minus x. And if you are going to get the same f of x function, f of x comma y, then we can say that function is symmetric about uh, y axis. The simple trick is, if a function has uh, x x variable whose power is even, then we can say that it's symmetric about y axis. uh, if you want to check the symmetricity about x axis, then just keep y is equal to minus y. Then if you're going to obtain the same function f of x comma y, even if you keep y is equal to minus y, then we can say that the function is symmetric about what we call x-axis. A simple trick to find it: if a given function has an y variables whose power are even, y power even, then it's symmetric about x-axis. If the given function has an even powers of x, then it will be symmetric about x-axis. If the given function has an even powers of y, then it will be symmetric function about x-axis. Yeah, quite opposite. I mean, if x even, then y-axis symmetric about y-axis. If y has an even power, then it's symmetric about x-axis. Is completed. Now we have to take about origin. Origin. Where is the origin is located? If a curve is like something like this, yeah, the origin is located at the midpoint of this curve, and that's what we can say, right? If a function is going to pass through origin, then in the f of x comma y function, we don't have any intercept. I mean, c constant value. It's going to be zero. Uh, in the previous video itself, we have discussed about asymptotes. We will try to check the asymptotes of an given function. Why we are checking the asymptotes mean, we will if a function is going to tend to infinity, to check its convergence, where it's going to like end, where this function is going to end. In that cases, we use asymptotes. Asymptotes are used for bounding the function, bounding the curve between the lines, and we have to check the points like uh, for this function, I have tangent at certain distance, and I have tangent at certain distance. These distances are symmetric. As the function is symmetric about y-axis, these distances are going to be same. Where this function is going to have an vertical tangent, it's a point, right? The point where it has a vertical tangent, the point where it has an horizontal tangent. We have to check these points. Yeah. What? Why we have to check about tangents, right? Why we have to check the tangent? If a tangent is going to be horizontal, that means the curve is going to just touch to it at that point itself. That's it. That means the function can't go above this line. Okay, this is the limiting value of that function. And if you have a tangent at this location, it is the lower limit, it is the upper limit. The function can vary between these. For boundedness, we use tangents, just like asymptotes. Asymptotes is nothing but tangents at infinity. And we will check the normals, point of contact of normals, and all these things in points. If we discuss a problem, I think you might get a clear idea about curve tracing. This is the basic mathematical intuition we have to carry out before tracing the curve. In this video, we will discuss about problem regarding curve tracing. Yeah, it is a typical problem regarding curve tracing in a Cartesian coordinate system. We have to trace this. function f of x comma y. Yeah, to curve and to trace and curve, we have to check about these four things as we discussed in the previous video. First thing, we have to check about the symmetricity, whether it is symmetric about x-axis or y-axis or something like that. And we have to check about origin, asymptotes, and points. We will go through each of the point one by one. First, we will check about check the symmetricity of a function. To check the symmetricity about x-axis, we have to keep y is equal to minus y. Yeah, if I'm going to keep y to minus x into a plus x, then we are going to get the same function y square into a minus x is equal to x square into a plus x. It is the same function, just like f of x comma y. Just what is it? F of x comma y. Both are same. So we can say that it's symmetric about x-axis. Yeah. We will check now. We will check the symmetricity about x-axis, y-axis. X equal to minus x. That implies y square into a plus x equal to x square into a minus x. It's the function what we are going to get if we keep x equal to minus x. It's not equal to f of x comma y. So this function is not symmetric about y-axis. Yeah, we check the symmetricity about x and y axis. Even if you're going to check about x equal to y, it's not going to show you the symmetricity. Now we have to check the presence of origin, whether is it passing through an origin or not. Yeah. We can simply say that this function is passing through origin. Since there are no constant functions, constant values in the given function, we can say that this function will definitely pass through origin. Yeah, this function passes through origin. Then we have to check about the asymptotes. Uh, by seeing the problem itself, we can say that this type of function is going to have only asymptotes which are parallel to the axis. Uh, because we don't have here what we call the highest, the power of what we call the degree of this function is 3. Here no, we have nowhere y cube and x cube. Yeah, we can get x cube, but here we can find we cannot find y cube. So these type of functions can't have uh, oblique asymptotes, right? Now we are going to check the asymptotes of this function y square. It's the highest power of y, and a minus x is the its coefficient. We are going to equate it to 0. Then we will get x equal to a. X equal to a is an asymptote. Yeah, let let it be x equal to a. Let it be x equal to a, and the curve reaches it touches it infinite at infinite. Whether it can be this side or it can be this side. We will check the limits of x and y values now. Now another thing we have to check is points where this function is going to cut the x-axis and y-axis. I mean, it's definitely going to cross at origin. If you are going to keep y is equal to 0, then we will get all the points where the function is passing through x-axis. Just keep y is equal to 0, then whole left hand side will be 0. X square into a plus x equal to 0. That implies x square equal to 0 and a plus x equal to 0. Because x square cannot be, I mean, it's always a positive value. Uh, this function can be 0 when only when x whole term is 0. So I'm equating x square as 0. X equal to 0 and x equal to minus a. This function crosses, I mean, passes through x-axis at x equal to a. X equal to minus a. Let it be x equal to minus a. This function crosses the x-axis at x equal to a. That's what I mentioned here. And we will check the when this function will cross through y-axis. We will just keep x as 0, a minus 0 plus 0 into a. That means y square equals 0. That implies y is equal to 0. That means only at the origin it's going to cross the what we call y axis. Just see, x equal to 0. We took x as 0 and we got y as 0. That means the function crosses y axis only at origin. As we know, the function is symmetric about y axis, x axis. Whatever the function we are going to get up, the same will be replicated down. Whatever the function we are going to get up, same thing will be replicated down. Now see, uh, by observing this function carefully, we can say that if x is going to be more than minus a, if this function is going to cross, that means if the function is going to come like this or going like this, just check what is the possibility. If it's more than minus a, this whole term will be negative and this term will be positive. Negative into positive will be negative. Here, as we taking minus a greater than minus a, the whole term will be something positive. Positive into positive. Here, left hand side whole thing has to be positive. But here, in left hand side we are getting negative value. Positive term will never be equal to negative term. So we can say that x values can't be greater than minus a. That means the function will be bounded between uh, x equal to minus a and x equal to a. And at x equal to a, it touches, it goes to infinity. That means the function has to pass through origin and it touches this line at infinity. Yeah, same thing has to be replicated. Uh, Now, what is the shape in between? Here we have what we call square terms. Then it's non-linear. It's nothing like going to be uh, linear. Just it's not going to be a line. So we are going to get some curved function. Yeah, same thing has to be come down. This is how the original function of this. This is how the graph of the given function look like. This is how we trace this curve. Okay, guys. Thank you. This is all for this video. Meet you in next lecture. Bye.